Lucas. I'm a cytogenetics technologist at Oregon Health and Science University Cytogenetics Lab, at night diagnostic labs. Yes, that is a mouthful. They make me say it all because we don't want to leave anything out. So in any case, I'm here today to talk about just the basics of cytogenetics. There's so much to talk about, and 20 minutes would never cover it all. So we're just going to see how far we get. I'm going to basically first, the main focus of the talk is going to be on constitutional cytogenetics, and constitutional meaning what you're born with. There's a whole different branch of cancer cytogenetics, and you may see a few slides that relate to that, but the bulk of what I'm going to talk about will be just the stuff you're born with. Excuse me. So, let's see. Nope, that way. Well, this way. Which way? Oh, it's going to be, there we go. So, cytogenetics is the branch of genetics that focuses on the examination of chromosomes to identify structural changes that result in abnormalities that we are born with or that we acquire over time. Patients are often referred for cytogenetic analysis due to birth defects, developmental and or intellectual delays, disabilities, infertility, recurrent miscarriages, and cancer. This is by no means an exhaustive list, but they are some of the more common reasons for referral that we see in our lab. The finding of a chromosomal abnormality can be very critical for the correct diagnosis and the proper medical plan of action for the patient. Okay. So what is a chromosome? It is an organized thread-like, tightly packaged molecule of DNA found in the nucleus of the cell, and it looks roughly like this. It has a short arm, which is referred to as the P arm, and a long arm, which is referred to as the Q arm. The pinched area that you see roughly in the middle is the chromosome centromere. So that's just really a very general image of what we're talking about. So where does a chromosome fall in the grand scheme of things in the human body? Your body is made up of tissues, which are made up of cells. Each cell has a nucleus, and the nucleus contains a complete set of chromosomes. Each chromosome is made up of one highly organized, highly compressed molecule of DNA. Genes are made up of DNA in a particular sequence and of a particular size. There are many, many genes on one chromosome, 20,000 to 25,000 roughly. And with that in mind, we're going to focus on the chromosomes. So before you can analyze for abnormalities, you need to know what normal looks like. And this is normal. I have an example here of both normal and male and female. On the left, we have normal female karyotype. On the right, we have a normal male. Generally speaking, we as humans have 46 chromosomes. In females, there are 23 pairs that are alike in banding patterns, including the sex chromosomes, with females having 2 copies of the X chromosome. In males, there are 22 pairs that are alike in banding patterns. However, the sex chromosomes for males are not identical, and males having just one X and one Y. These cells have been stained in Giemsa stain in order to visualize the unique banding pattern for each chromosome. X and Y chromosomes are called sex chromosomes, while the remaining 22 pairs are referred to as autosomes. As a cytogenetic technologist, I have to commit to memory the normal banding patterns for each of these chromosomes in order to be able to recognize when a chromosome has lost material, which is called deletion, gained material, which is called a duplication, or has a rearrangement that could be the cause of a disorder or disease that the patient is presenting. And now that we see what qualifies as normal, we can take a look at the different types of chromosomal abnormalities. So one of the first things that we look for is copy number change. Have we lost or gained any genetic material? Well, there are different ways that copy number changes may present themselves. We may see an extra copy of the entire genome. We may see a gain or loss of the entire genome, or we might even see smaller gains or losses within an individual chromosome. Let's first start with the whole genome. In this instance, you're only going to see gains. Here we have 3 copies of every chromosome, and we refer to this as triploidy. Generally speaking, this abnormality is incompatible with long-term survival, and the results are multiple and often severe birth defects. Most often, triploidy results in early miscarriage. Here we see 2 examples of whole chromosome change. On the left of chromosome 21, which is also known as Down syndrome. On the right, we have a copy number loss of the 6th chromosome, and that leaves us with 1 copy of the X chromosome. This one is commonly known as Turner syndrome. First, we'll talk about Down syndrome. These individuals have characteristic facial features, including a flattened profile and nose, small head, ears, and mouth, upward slanting eyes, often with a skin fold that comes out from the upper eyelid and covers the inner corner of the eye, as well as sometimes they have an oversized tongue. They also may have anomalies affecting the heart, lung, and gastrointestinal tract, increased risk of developing leukemias, immune system defects and deficits, and often, but not always, they exhibit developmental delays or disabilities. Here we have an example of a whole chromosome copy number loss, where we're missing a whole 6th chromosome and are left with only 1 copy of X. This is also known as Turner syndrome. These individuals often have shorter than average height, low set ears, webbed neck, infertility due to non-functional or absent ovaries, frequent ear infections in childhood, cardiac and renal defects, and these patients may require hormone treatment to develop a more female physique. Here are some examples.
They're usually in women?
Yes, yes, they're always women.
Okay.
Mm-hmm. They always present as women, but they sometimes will have a more masculine appearance, you know, the lack of curves as a result of their ovaries being hypofunctional or just not there.
Right.
So,
so only women have the Turner syndrome, is what you're saying?
yes.
Okay.
I mean, if you're going to lose a Y, you're going to be a female anyway, because your sex determining region for male development is on the Y. So if your Y is gone, you're going to default to female no matter what.
Gotcha.
So 1 X is not enough to be a female.
Well, you will look female.
Okay.
Your physical, you will present as a female, yes, but it's basically the karyotype is 45XO or just X, 45X. You're just minus the 1, but you can't have any male physical characteristics without your Y chromosome. Here are some examples of copy number changes within chromosomes. The one on the left is a karyogram of a patient with Wolff-Hirschhorn syndrome. It's associated with deletion at the end of the P arm of chromosome 4. In karyogram on the right, we can take a look at chromosome 15, which is a small duplication close to the centromere on its Q arm. I don't know if you can see that little duplicated area up there. I don't have a pointer. Can you guys see it?
At the top?
The one on the one that's circled?
Oh, yeah.
Yeah, that guy right there. He's bigger than his friend on the left.
Yeah.
They should be identical, but they're not.
Okay, okay.
You can see like near the centromere, which is up at the top, this is an achocentric chromosome, which means it's got more Q arm than anything. There are like 3 distinct chunks of light banding region on the right-hand one near the top. But on the left, you only see 2. Can you see what I'm talking about?
Yeah.
Yeah, so the one on the right is duplicated. You should only have the 2 big chunks of white on the left. This one has 3. So, and this small duplication close to the centromere on this Q arm is sometimes associated with autism spectrum disorders. Let's see, where did my pointer go? There it is. It's trying to run away.
What do you,
yes?
do you do you guys study autism too as a part of your overall?
We have very many patients that come in to see us. I mean, we don't see the patients themselves. We get their samples. It's usually blood. We're looking at chromosomes from the lymphocytes of the blood. And we will get a whole range of referrals for autism spectrum disorder, developmental delays, receptive expressive language delay or disorder. Any description of anything on the autism spectrum would referral for to see if any chromosomal abnormality. That said, this particular abnormality is not the only abnormality of chromosomes that could result in symptoms that could be classified as autism spectrum phenotype. This is just one of them.
I see. Okay.
And some kids don't have chromosomal changes that we can see. Some kids may have mutations, which is on a smaller level. It's a molecular level where you would want to do sequencing, and that's a whole nother talk. And that would be a lot smaller. Some kids don't have any chromosomal abnormalities and they still develop autism. So this is obviously a developing field, and we're learning more all the time about that. And it's very complex. It's not a very simple subject matter.
Can you like change the chromosome, or it's just discovery?
Well, the change occurs during development, you know, in utero. I mean, it's what their parents gave to them. Or sometimes the change is de novo, meaning it's something that didn't come from the parents. There's something happened in the developmental process in the womb that created that situation.
But there's no way to change therapy, whatever, to change it, whatever.
No gene therapy at this point, no.
So, do you know the ages of the person, you know, whose blood you're looking at?
Yes.
You do?
Yes, we know the ages.
Have you ever run across, I'm sorry to push this out.
No worries.
Have you ever run across a blood sample of a child who was diagnosed in his early teens as opposed to when they were small?
Yeah, sure. And that happens a lot of times because we'll get referrals from outside the Portland metro area. We get samples from all over the place. Sometimes people got a diagnosis early of something like developmental delays. You know, the technology that we use to detect this is still developing. I mean, what I'm showing you today basically are G-banded chromosomes, and they have a resolution limit down to 5 megabases. Our newer technology, which is microarray technology, and that's my section in the lab, we have the ability to detect down to, you know, 300 kilobases, which is really small. You'd never see it on a chromosome. And so we're able to pick up some of the abnormalities that were previously missed. For instance, that patient that you're talking about who's 16 may have gone in for, you know, when he was born and only gotten chromosomal analysis because that was the only thing that was available at that time. But now the newer technology has emerged of microarray, and a lot of those patients we're seeing again because they were previously called normal, but it was only because we couldn't see it at that resolution. Microarray has an incredible advantage over just general karyotyping because you can see smaller regions more clearly.
Yeah, the one I'm talking about is 13. So
it
seems to me he underwent, this is somebody I know personally, underwent a personality change rather than always being that way.
I am by no means an autism expert.
I know.
But that sounds highly unusual.
That's what I thought. Okay, thank you.
Yeah, sure. No worries. So now we're going to talk about, we'll continue talking about copy number change within the chromosome. This little boy, no, girl. I had to look at his karyotype. This little girl in front of us has Wolff-Hirschhorn syndrome and is Her situation is characterized by a loss of genetic material at the end of the P arm. And here we can see the typical facial characteristics in the picture. These patients often display delayed growth and development, impairment of verbal communication and language skills, low muscle tone, and are prone to seizures, may have microcephaly, which is basically a small skull, and short stature, and some skeletal anomalies.
So could it be like a person have this 4P have problem, but didn't have the syndrome, didn't have the disease? Could that happen?
There's a specific gene in that region that has to be deleted in order for this phenotype to show up, and that's on a smaller scale. This is how we see it when we see it on chromosomes. We could probably detect a smaller deletion, again with microarray, which is the newer technology, and we could see the software that we use in microarray helps us see exactly which genes are within our deleted or duplicated area. So we would be able to see that specific gene that's affected and see if it's had a copy number change very easily. So, okay, so we're coming back to the autism spectrum piece of it. This is a duplication, again, a small duplication on the Q arm of chromosome 15. And I think, like we were all talking about earlier, this is basically a neurobehavioral syndrome characterized by difficulties with social interaction, impairment of receptive and expressive communication skills. We have these stereotypic and repetitive behaviors, and most of the time we're catching this before 3 years of age. You may see it later, especially for people who might be in outlying, more rural communities and don't have good access to health care, but that's becoming less and less as, as our metro area spreads and people are able to get in and get referred for a genetic workup. Here we go. Did I lose one? There we go. Dun, dun. Okay, so not only can we have extra or missing chromosome material, we can also interrupt important genes. We can have translocations, which is when two different chromosomes exchange segments with each other. These come in two different flavors. Balanced translocations result in no overall gain or loss of genetic material, but important genes can be disrupted. There may be a danger for these folks that have these balanced translocations. They may not know that they have it until they have offspring with an unbalanced result. And then they go in for genetic counseling for their child, and a lot of times when we find abnormalities in the children that are unbalanced, we'll say, hey, we would like to have the blood of mom and dad. So we can figure out where this is coming from, and this is important because this may help with future pregnancies. Sometimes these unbalanced translocations result in multiple miscarriage, which is why we get referrals often for recurrent pregnancy loss. Because sometimes these parents, one parent is carrying a balanced translocation, but when they go through the reproductive process, the combination produces an unbalanced offspring. Sometimes they're viable. They just have that abnormality. Sometimes, if it hits in the wrong gene, they just have a recurrent pregnancy loss.
So does it usually when you see that happen, or when you know of that happening, is that when like they just fail to develop in utero, or?
Yeah, they just get to a certain point and can't go any further. I mean,
okay.
It's just not, it's not compatible with life.
Okay.
It's missing something that it must have to continue forward.
Okay.
So, like I was saying, the unbalanced translocation can result in an overall gain or loss of segments of genetic material. often with serious negative effects.
10 minutes.
There we
There's
go.
a 5-minute warning.
Another type of rearrangement is an inversion, and there's no overall gain or loss of genetic material. But again, when rearrangements occur, you can disrupt an important gene because those breaks can happen in the middle of a gene. And if it's a gene for hair color, who cares? But if the gene for kidney development, that would be a problem. That would be a bad thing. So
Okay,
you
wait,
just
wait.
never know.
Back it up. You fuzzed out. I heard
Fuzzed
something
out?
about
Okay,
hair
what'd you mean?
color, I think. I don't know.
Easy, all black.
Nancy, you want to change your hair color?
I said, you know, if a gene is interrupted and that gene codes for something, you know, really not important like hair color, unless you're just dying to be a blonde, but you know, it's not going to be important, but it could, a gene can be disrupted, and that gene might code for, say, kidney development.
Gotcha.
That could be a problem.
That could be a big problem. Yeah.
Yes, yes. Or
And then all the Chinese have the same gene, the color section, because we're all black.
yeah, it's all good. You know what to expect.
Yeah.
Okay, so we are up on time. Obviously, I'm being blinked at right now. So the technology that I've been showing you is basically G-banding. It's one of the older techniques that we use to analyze chromosomes for gains and losses. There are other
5 megabytes.
technologies that are available within our cytogenetics lab. There's fluorescent in situ hybridization. That could be another talk in and of itself. It has to do with glowy things. And if I can find a picture, let's see. Here we go.
It's like a 3 billion genes. That's I know.
It's a lot. It's a lot of stuff. Very, very quickly. And there are single-stranded DNA probes that are tagged with a fluorophore, which can be seen using a fluorescent microscope. The patient cells are set in place on a fixed slide. The binding process between the patient's single-stranded DNA, which is already affixed to the slide, and the single-stranded fluorescent probe, which is subsequently applied to the slide. I'm sorry, I'm starting to
Mush.
rush.
You got 5 minutes. How many more slides?
A lot, but I'm going to go through them really fast. Once your sample is affixed to the slide, I don't know why that's marked. Oh, my arrow is just in the wrong place. Sorry. You denature the DNA, which is native, you know, in its native form is double-stranded. You make it into a single-stranded form during this process, and you apply the fluorescently labeled single-stranded DNA probes to the slide. The single-stranded probes have a specific sequence that only bind to single-stranded DNA that is complementary to that sequence. They're mated. They match each other. I don't know if you remember your 4 bases when we're talking about what makes up DNA. You've got adenine, guanine, thymine, and cytosine. And adenine and thymine only bind to each other. They're complementary binders, and guanine and cytosine bond to each other in a complementary fashion. So we have a complementary single-stranded DNA sequence, and if that sequence does not exist in the patient sample, it won't bind to the slide, which indicates that the patient has a deletion in that region. So you see here a pattern which shows aqua and red. So the aqua is basically the control probe letting you know, okay, you do have 2 copies of this chromosome, but you see here we only have 1 copy of red. So that means that the gene that we were looking for on that chromosome is only present on 1 chromosome. It's not present on both, so they have a deletion. Does that make sense?
Yeah, there's a deletion.
All right, let's see.
Then there's extra kind of thing.
Let's see. I'm trying to figure out where I left. Okay, so my baby is array comparative genomic hybridization. ACGH, that's right. It covers the entire genome like karyotyping, but you can detect deletions and duplications at a much higher resolution. Kind of like FISH, but better because it covers more areas. FISH covers only specific small segments. Microarray covers the entire genome.
Okay.
So so the advantage is that you can have an exact start and stop coordinates for your deletion or duplication and know down to the individual base numbers. And that means you know the exact size of the copy number change that you have. What it can't do is detect balanced rearrangements, because all it's made for is detecting gain or loss of genetic material. You won't see balanced rearrangements because all of the DNA is there. It's just in a different place with a rearrangement.
So rearrangement, this one cannot detect.
Not if it's balanced, no. If you have a net gain or loss somewhere as a result of an unbalanced translocation, it'll tell you that something's gained or lost, but it won't tell you that it's a result of a rearrangement.
Oh, I see.
That
So
you'd want to get maybe parental samples.
We call the variant in the gene when I'm doing that. That's some kind of changes in the position.
So the
There's
number
a reference gene, right? Reference gene.
reference DNA we use.
Yeah, reference DNA.
We compare it against the patient's DNA in this particular technology. The normal DNA has all the normal copy number of genetic material. You compare it to your patient sample. If the patient has more in one particular area than the reference DNA, then it's going to show up as a gain on the microarray.
Okay. So this is
readout.
all compared with the reference. Okay.
Somehow one of my slides got ditched in this whole process. In any case, I wish I had well, there is a whiteboard. Look at that. But that's not going to show up very well, is it? It'll show a gain or a loss, but not a balanced rearrangement, and it shows very, very small segments. Another thing microarray can do, which is really, really cool and I love, is not just to do with copy number, it has to do with detecting lack of heterozygosity. So you have one copy from mom, one copy from dad, right? Sometimes if you're, shall we say, too closely related, the copy that you have and your mate have might be of the same type. And when you come together and have children, it's called homozygosity. There's no difference, you know, if your family background is closely related. And basically I'm talking about a couple of situations, one being consanguinity, the other being something called identity by descent. Identity by descent means roughly that you're in an isolated population and you can't get out and breed with other people. And so basically your genetic pool is kind of shallow because you can't get out and bring in fresh material, for lack of a better word. So in that community, you might have a lot of similar versions of genetic material, which is not always a bad thing, but if, say, you and your husband are related somehow, you have a mutation in your genetic code that has been covered up by the other side because you yourself are heterozygous in that region. But if you pass on a recessive mutation and your husband has that same recessive mutation because you have a common genetic background, that recessive mutation will no longer be covered up by anything else. And it will be expressed in your offspring. And that may be a bad thing if it's a disease, if it's in a disease causing area in a gene.
Like one from the Queen Victoria.
Yes, exactly. That is exactly the problem. Hemophilia was one of those types of things. Yeah. That's as good as wrapped up as it's going to get.